Hi, I'm Liang Sun. In this short talk, I will give a very brief introduction to Diophantine problems, which concern about integral and rational solutions to systems of polynomial equations. Diophantine geometry is the study of Diophantine problems by means of geometry. More explicitly, we may first understand those solutions in an algebraically closed field. Sets of such solutions are known as algebraic varieties, which are the target of the classical algebraic geometry. Then we restrict ourselves to those solutions in arithmetically interesting domains, such as the integers, rational numbers, and their generalizations. It is the goal of algebraic number theory to understand these domains via the techniques of abstract algebra. In other words, Diophantine geometry is the investigation of the arithmetically interesting points on an algebraic variety. The first question might be, are there really such points? For example, how to determine whether or not an arbitrary algebraic variety X over a number field K has a point over K? This task may be difficult, as indicated by the negative answer of Hilbert's 10th problem, which says that there exists no algorithm which can decide the solubility in integers of every system of polynomial equations with integer coefficients. However, some conditions which imply the absence of rational points can be checked by algorithms. Such conditions are referred as obstructions to existence of rational points. For example, one may view K as a subfield if it's the completion with respect to a non-trivial absolute value V. Then we clearly have Brown implication. Considering all such V together, we see that the absence of K rational points on X can follow from the orange condition, known as the local obstructions to existence of rational points. When local obstructions is actually equivalent to the absence of rational points, we say that Hasse principle holds. Hasse principle holds for algebraic curves of genus 0, but fails in general. Manin developed a theory to explain the failures of Hasse principle. Using both number-theoretic and geometric tools, he constructed the Brauer set of X, such that the red condition, known as Brauer-Manin obstruction, implies the absence of rational points on X. Actually, in all counterexamples of Hasse principle known in that time, the Brauer set is empty. For curves, it seems that Brauer-Manin obstruction is always equivalent to the absence of rational points. For those with genus bigger than 0, Sirashkin found a reformulation of the Brauer set in terms of an object with an easier construction. Starting from the PhD thesis, many of my research works focus on certain generalizations of this object, mostly with the number field K replaced by function fields. Many statements in Diophantine geometry reflect the principle that geometry determines arithmetic. For example, an algebraic curve over a number field, with genus greater than 1, has only finitely many rational points over this field. It's Faltings proves this statement, known as Mordell conjecture, in which we note that the genus is a geometric invariant of a curve. We may rephrase Faltings' theorem by saying that, if the intersection of an embedded curve with a set of rational points on its ambient space is infinite, then the genus of this curve must be 0 or 1. Such a statement is in the framework of so-called unlikely intersection with the following philosophy. A variety containing too many arithmetically special points must be geometrically special. If this philosophy is considered for integral points on algebraic varieties, we get a conjecture of Lang and Vojta. My co-authors and I have some results on this conjecture over function fields. For other examples, theorems on unit equations in Diophantine approximation can be interpreted as statements of unlikely intersection between additive group varieties and multiplicative group of points. I have investigated the situation where the roles of addition and multiplication are interchanged. Similar philosophy also occurs in problems without involving geometry. For instance, Pisotti's root conjecture, proved by Zanier, deals with linear recurrences containing too many terms which are D's powers in a number field. With my co-authors, I did some investigation on its function field analog. As you may have noticed, I worked mostly on Diophantine problems over function fields. The translation of number field problems to their function field counterparts is motivated from the following fact. There is a strong analogy between number fields and function fields of smooth and projective curves over a fixed perfect field, small k. The analogy is especially good when small k is finite. I worked a lot in this case. For more details, you may look at the nice table in section 2.6 of a paper by Poonen through the QR code on the slide. Thanks for your attention. If you look for more information about my research, please visit my homepage through the QR code on the slide.